So whenever we want to create something or destroy it, we use a small vk, because again, these are functions we created with functions we create and destroy Vulkan objects. We use the create and destroy, and then it's like whatever name of the object. If we are querying Vulkan for info, basically want to get information about, let's say, our hardware, uh, and how compatible it is with Vulkan, we usually use vk enumerate or vk get. We have vk allocate and vk free and vk map and map. These are usually related to the GPU's memory allocation and freeing, and the ability to map regions of that memory that can be used by the GPU and the CPU altogether. We'll look at this once we get to the memory part. Then we have like VK set reset. Basically, these I've encountered these only in the case where we are using semaphores, and semaphores are something like synchronization primitives. We'll look at them again later. Then we have VK commands. These are all of these are functions that can be recorded to a command buffer, and we'll look at command buffers again later on. But basically, uh, all the things we ask the GPU to do, we have to do it through these command functions that are recorded to the command buffer. And the only way to record them again is to vk begin, vk end. That's the only way. Bind, flush, and invalidate. These are again memory related stuff, although bind we can see it in the pipeline, but basically you can think it as memory related. Another common things that I won't be touching is the allocator and the S-type. Allocator is a variable that we can pass to create or destroy functions. It basically allows us to pass our custom allocator, memory allocator. Let's quickly read my notes. All vk create or vk destroy functions have an vk allocation callbacks pointer. Basically, this is a function pointer called allocator. This allows us to use our custom allocator function. Custom allocators are good for tracking memory usage and performance, and not only tracking performance, but for increasing performance depending on the type and use cases. I did manage to find online some, I think maybe good examples of memory allocators, and they're in C++, so still there is a part where each allocator is explained in the document, so you can read it here. And this is a dash, not a dot. In the end, we should note that if you pass null to this allocator pointer, Vulkan will just use the system memory manager through malloc, which again is not ideal for when you're starting and learning. Probably is the best thing to do because you don't have to care. But yeah, maybe it's not a good thing for your final if you're doing some kind of a project with Vulkan. Maybe it's good to have an allocator, because memory allocations, once they can fragment, they can be very fragmented. Therefore, you can have cache hits and misses, and this will impact performance. S-types. S-types are basically related to structs. Every struct will have a field, like the first field of every struct will be this S-type. And I'll quickly read my notes. So this is part of structures. It identifies the struct in the API. Although this is annoying, and this is really annoying, to enter it every single VK struct, it solves these issues. One, debugging. We, of course, Vulkan can immediately know that we have passed the wrong struct to it and will notify us. And second is memory safety, because it prevents the API from writing to incorrect memory address. And basically, the S-type is as I said, it's an identifier that will help Vulkan access correctly the memory that the struct has. And now at the end, I would like to have a quick like overview of the workflow of Vulkan, mainly because or how we will proceed in these tutorials. Mainly because I think most tutorials, like, they start looking at Vulkan, but you don't know well, you haven't been presented with where exactly you are on this whole path from let's say the initialization of the instance to the final thing rendering on the screen. So like I made this quick map. Basically, we start with the creation of the instance, the Vulkan instance, and we will look what the instance actually is. And once we have the instance, we create the debug messenger in the surface. Basically, I see this as a first initial stage, and the debug messenger is quite self-explanatory. The surface, however, it's not. It's basically the window we'll be drawing to, and there's some steps in creating that. And in this, we'll see in the first video, actually the next video, we'll look at these three elements. So once we have the instance, we can get information about the physical device, and once we have the physical device, we can create the logical device. Now, the difference between the two is basically in the name. The physical device is the actual hardware, and the only thing we can do is actually ask that hardware, okay, what do you support? How many shaders you can support, how many images you can support, and so on and so forth. And the logical device, I see it basically like a connection or a link to the physical device. So once we have like the logical device, excuse me, we can send the information to the physical device, basically the GPU, to calculate our stuff. So once we have the logical device and the physical device all sorted out, we branch into two possible paths that in the end they branch together. But basically we have the resources, which are buffers and images. We have to create these. Basically these are data that we want to perform some operations on, and something that I call, and the next bit is something that I call the job system. And the job system is basically, okay, we have a connection to the logical device, but we okay, I lost my train of thought. But we have the connection to the logical device, but there is no way to give it like commands, and the only way we can do it is by creating queues. Now, the physical device, there is a connection between queues and how the physical device operates, because some GPUs don't have as many queues, some do. We'll look at this later on. But basically we have to create queues, and we have to create command pools and command buffers, and the point is basically to create command buffers, and these command buffers are submitted to these queues, and the queues then submit the information like one after the other to the physical device. So the command pool is basically there to manage our command buffers, and the command pool is basically if you know anything about memory allocation, like we talked about the allocator, which basically a pool is a type of memory allocator. Okay, so another part is the synchronization of the queue. We have semaphores, fences, and events. All of these three give us the ability to synchronize work between the GPU and the CPU. And another thing to mention that is that while command pools are, how should I say, directly connected to the queue, because you can only submit a command pool command buffer if this buffer was created on this queue, on its queue. Synchronization is not like this. Semaphores can exist outside of these relationships, but for myself and for my sanity, I guess, or the way I explain it for myself, I just group them into basically if I have a structure called queues, and one part of it will have like semaphores, fences, and events. We'll look at synchronization and watch what each does, like the semaphores, the fences, and the events. But for now, this is just like our overview. So once we have our resources, we have a job system to submit to the physical device. We perform actions. And the actions are either direct commands or passing our resources through a pipeline. And we'll look at pipeline again. Pipelines much later. But direct commands are like let's say we want to fill the whole buffer with zeros or images, or an image with a, let's say, black or blue color. And at the end of the actions, we have, once we perform the actions on our resources, we have like a choice to store the result to RAM or disk, or to present to the screen if we have like an image. We can present buffers because in the end, the image presented to the screen is just a buffer, but we'll talk about this later. And here I just made a quick overview of what these actions look like. Basically, we call the begin and end, which is these functions vk begin, vk end. We call them on, let's say, some command buffer, and we start recording commands. We have the direct command, like let's say fill, or we can call a pipeline, and we bind the resource to the pipeline, and we execute the pipeline. And at the end, or not, basically somewhere along the line, I just added it in the end, but it could be anywhere, we can add resource synchronization. And this is not quite like this. Not it goes a bit outside these. Events are closer to these resource synchronization. They're called pipeline barriers, but we'll look at them later on when we're doing like synchronization. But basically, we have to make sure that the pipeline at each stage access our resource in the correct format, or maybe make sure that nothing is writing to it. But we'll look this at when we're doing it, when we are talking about synchronization. And again, in the end, we just end the recording of the command. And when we end, this doesn't mean we have we have actually modified our data. We have to submit it to a queue to be submitted to a physical device, to the physical device, and only then we can get our data to be modified. So in the end, we submit it to a queue, and this is basically the end of our action. Then we have to store it or present it to the screen. But yeah, this is basically all there is to it. Another thing, maybe it's important to mention, is that let me get some writing. Okay. So another thing to keep in mind is the way to think about all of this. Basically, why do we need synchronization? Is basically because we have how should I say it? We should think of Vulkan API as doing a multi-process processing, not multi-threading, because in multi-processing we share We do not share the memory. In multiprocessing, we share the memory.